Photoelectric effect. This is a very important chapter and very easy chapter in grade 12. So let's look at the definition, or let's look at the definition of the title itself. You can see there, it tells you that photo means light, and electric on this title, it represents the electricity. So basically in this chapter, what we do, we are using light to create energy. It's a very good principle that is used in the solar energy industry. So we are using the light energy to electrical energy. The law of principle of energy says that the energy cannot be created nor destroyed, but can merely be transferred from one source of energy to the other. So light has what we call the dual nature of light. What does that mean when we say the light has a dual nature? Light can exist as a wave, and light can also exist as a particle. Light can exist as a wave, and light can also exist as a particle. By wave, that's where we will talk about the reflection of the light, the reflection of the light, and all that. And when we're talking about the photoelectric effect, is the other side of the light, which is the light exists as a particle nature. I hope that makes sense. So before we go far, I want us to remember that we also have what is called a visible spectrum. As visible spectrum, which other people refer to as the Roig beef, where R stands for red, O stands for orange, Y stands for yellow, B stands for blue, E stands for indigo, V stands for violet. These are the visible spectrum. Are the colors of the light that we can see with our naked eyes. We also have, just before the red, we also have what we call the infrared, which is what is used by most of our cell phones. It has a very low frequency. We also have on the spectrum the UV lights. We have X-rays. We have the gamma rays. And as you move from left to right, you are increasing the frequency of that light. And as you move from the right to left, you are increasing the wavelength of that particular light. So frequency is inversely proportional to the wavelength. If you can remember, the frequency is equals to the speed of the wave divided by the wavelength of that particular wave. In Doppler effect, we have learned that the speed that we are talking about will be the speed of that particular wave in a medium, but in Doppler effect, in this photoelectric effect, we are going to be speaking about the speed of light in a vacuum, not in a medium. I hope that makes sense. Now, like I said, that the light has a dual nature. So that dual nature of light, let's say suppose we have light rays like this. We have light rays like that. In theory, in that particular light rays, we have a group or a packet of energy that we refer to as photons. We have a pocket of energy that we refer to as photons. Right? And this particular energy, photon, it's related to the frequency of light and is directly proportional to the frequency of light. Meaning, so like I said, if we are going there, we are increasing the energy, we are increasing the frequency, meaning the violet The violet will have the highest energy as compared to red. The violet light will have the highest energy as compared to the red light. And the yellow light will also have the highest energy as compared to the red. Meaning on this red beef, red light will have the lowest photon, which is the lowest or minimum energy. I hope that makes sense. So now, let's suppose we have a metal surface. Let's suppose we have a metal surface. And in this metal surface, we have electrons. In every metal surface, we have electrons. Or in any particle, we have electrons. But these electrons are at a rest. Remember when we studied the electrostatics, the study of electricity, or the study of electrons at rest. So at this point, we have that metal plate there, and this metal plate, all the electrons that you see in red, they are stationary, they are at rest, they don't move. As you shine this light there, as you shine this light there, as you shine that light there, that there will be a movement. And that's what photoelectric effect is all about. Alright, when you shine the light on the metal, when you shine the light on the metal, the electron will reach a state of excitement and they'll start jumping around. And if the energy is greater than what we call the work function, the work function is the minimum energy on this metal that is required to get the electrons to be ejected from its metal surface. The work function is the minimum energy that's required to emit the electrons from its metal surface. So if we are shining a light, or what we call to sometimes as incident light, on that metal surface, if that energy is enough, the electrons will be excited, they will be ejected, and if there's enough energy, they will start moving. They will start moving. And when they start moving, that's when electricity is generated. That's when in solar we are saying this solar is producing electricity. Now, we have two metal surfaces. We have the one with the blue light. Don't forget the roach beef. We have the ones in the blue light, and we have the red light. So if this metal is exactly the same, we're expecting that the blue light is going to be the one being able to eject the electrons from its metal surface. We will see. So that energy there in that incident light is calculated by Planck's constant, multiply the speed of the light, divide by the wavelength. The energy is also equals to E equals to frequency. Planck's constant multiplied by the frequency. And we know that the frequency is the speed divided by the wavelength. I hope that makes sense. This H is also what we call the Planck's constant. Now, there are two things